Hello, everyone, and welcome back. We're going to be doing systems of equations today. We're going to be looking at two different equations. They're both labeled y, or they're both y. I'm not using function form yet, but I did color them different colors. You'll see why in a second. As you guys can see, I've laid out my xy plane, my Cartesian plane. Once again, named after Rene Descartes. Just a second. Before we get started on systems of equations, a little bit about Rene Descartes, French philosopher, 17th century, that means the 1600s. Prior to him, geometry, shape-based mathematics was the standard. After him, algebra. So he came up with a lot of concepts. The most important of which, that I guess for anyone in algebra 2, is he came up with this concept of knowns and unknowns. So as you guys can see, I put the unknowns, the variables that we call variables. I put the unknowns, the y and the x squared, the x, or if you're looking at a linear, as we're at right now, y is equal to mx plus b. The y and the x are unknowns, and the m, the slope, and the b, the y-intercept, those are both knowns. So just an interesting little tidbit. Cool dude, French philosopher, not just mathematician, also scientist. Also, he served in the military. Dude was a Renaissance man. Rene Descartes. Check him out. Descartes. The S is silent. Check him out. But back to the systems of equations. We're looking at our two-dimensional plane. That means our flat plane, our x, y plane, our Cartesian plane. And we're going to graph this line, this linear relationship, and this line, this linear relationship. This first one I'm going to use, they're both in slope-intercept form, but I'm just going to do it for the first one. The first one, I'm going to use my shortcut. I'm going to find the y-intercept. That right there is my b, and b is my y-intercept. So that's positive 5. Right there. I'm going to put a point right there. I only need 2 points to make a line. So I just got to find one more point, and I'm going to use the slope now, the slope of this line. Which, if you remember, is also known as the rise over the run. And the rise is the change in y. That triangle is a delta from the Greek. It just means change. The change in y over the change in x. But let's focus on rise over run. I feel like that's the least confusing way of thinking about slope. Just forget about everything else if that stuff's confusing. Rise over run. So what is my rise? In this case, it's negative. So I'm going to go down 3. 1, 2, 3. Right there. And then I'm going to go over 2. Positive 2. So 1, 2. Right there. So this is where my second point is going to go. And that's all I need to plot this line. So let me grab my trusty ruler. Awesome. Line 1 of 2 done. And now this other method is slower, but when you guys get to more advanced equations, more advanced relationships, like quadratics, exponentials, this method can come in handy. It's good to know. So let me just do this alternate method here. It's my table method. I got my x and my y. I'll pick a point, 2 points. I'll pick 2 points, and first I'll put in the x coordinate. So let's do 0, and let's also do 5. So when x is 0, what is y? When x is 0, y is going to be 2 times 0 minus 1, which is just 0 minus 1, which is just minus 1. So when x is 0, y is minus 1. Makes sense, right? That's our y-intercept. Okay, sorry, I'll keep going. How about when x is equal to 5? What is y then? 2 times 5, just plugging in for that x. 2 times 5 minus 1. That'll be 10 minus 1. which is 9. So when x is 5, y is 9. So I'll go over 5. Let me write each of these points out. This is I'll do this 0, -1, 0, -1 right there. The x comes first, then the y. 0 movement left and right, 0 movement on the x, but down 1. Down 1 on the y. Okay, my next point is over 5. X is going to be over 5, and then up 9 for y. So actually right there, let me erase my table. Over 5, up 9. And that's my 5, 9. And now I have those 2 points using this table method, a little slower, not as fast, but more guaranteed to work over time. By over time, I mean when you encounter more advanced relationships. And boom, you got your 2 lines. Now, we've already covered this stuff. We've already covered linear graphing. So why are we covering it again? Why are we doing this again? Well, I did give you guys just a little review just now, but the point of this is to look at these relationships and where they intersect. Intersection points are going to be big in mathematics, where 2 lines intersect, where a quadratic parabola, where a parabola intersects the x-axis or the y-axis, or another parabola. Those intersection points are important. So this is your first exposure to something that's going to come up throughout algebra and calculus and more advanced forms of mathematics. So we are focusing on that intersection point. Now, visually, it's right above that blue dot that I mean, I might have drawn this wrong. It might actually be right at that blue dot. But how can we be sure? This isn't graph paper. I drew my own axes. They might not be drawn perfectly to scale. I mean, in all likelihood, they're probably not. So how do I work with these 2 linear relationships visually represented here? Well, let's work with them algebraically. Let me write them down over here. So I got y is equal to -3/2 x plus 5, and y is equal to 2x minus 1. Now, let me show you guys a little something. Now, first off, this is a concept that you don't really need to go too far in depth, but I'm still going to mention it. Because of the particular theory known as the commutative theory, -3/2 x plus 5, and I'm sorry, it is not the commutative theory. I think it's the associative. I'm going to Google that and get back to you guys. Don't quote me on either one. But the concept is if A equals B and B equals C, A equals C. So if -3/2 x plus 5 is equal to y, and y is equal to 2x minus 1, well, let's just cut out the middleman. This is my A equals B equals C. Well, A equals C. So -3/2 x plus 5 equals 2x minus 1. I've substituted in this 2x minus 1 for that y, or if you want to look at it the other way, that -3/2 x plus 5 for that y. And now I can combine like terms and solve this. So let me subtract -2x here, and that'll get me -3/2 x minus 2x. I'm going to go fast here, so just remember that minus 2x is really minus 2 over 1x. Minus 2 over 1x is just minus 4 over 2x. because if you take that 2 over 1x and you multiply it by 2 over 2, it doesn't change it because 2 over 2 is just 1, but it still allows you to manipulate the denominator. Some review right there. So that'll be negative 7 halves x. And I'm going to get rid of this 5 as well. I'm going to move that to this other side. Minus 5 to both sides. So that negative 1, those will cancel. So that'll be equal to, because these will cancel too. Negative 1 minus 5 is negative 6. Multiply both sides by negative 2. And we're going to be left with 7x equals 12. Divide both sides by 7. And we're going to get x equals 12 sevenths. We're not done yet. We got exactly where this intersection point is on the x-axis. What about the y? What do we do to figure out the y? Well, we got what x is equal to, 12 sevenths. Let's plug it in. Let's plug it in for one of these. Which one of these do we want to plug it in for? Negative 3 halves x plus 5 or 2x minus 1? Well, this is one less fraction to work with. So I'm going to use this one. I'm going to be lazy. So let's do that. Y, what is y equal to? Y is equal to 2 times 12 sevenths minus 1. So y is going to equal 24 sevenths minus 7 sevenths. Did that one pretty quick. Remember, this is 1 over 1 multiplied by 7 over 7. Anyway, enough with that. Y is going to equal 24 minus 7 is 17 over 7. And that's our y. That's our x. As you guys can see, visually, it would have been very hard to calculate that 17 sevenths and that 12 sevenths. So this is why this method comes into play. So our final answer would be the solution to this system of equations is a 12/7 and 17 sevenths. Right there. Cool. See you guys in the next video.